Did you ever wonder what combination of Mentos and Coke would give you the biggest explosion? Let's design an experiment to find out. In this episode of Design and Analysis of Experiments, we will consider one of the internet's favorite reactions: the rapid release of CO2 gas that occurs when Mentos is dropped into carbonated soda, Coke, Pepsi, or other types. Our goal is to determine what combination of factors leads to the biggest expulsion of liquid. The response variable will be the change in the weight before and after the Mentos is added. The factors that we'll be testing, or that we will consider, are going to be the brand, being Coca-Cola, Pepsi Cola, or the local Western family brand Kicking Back Cola. We'll also test the variety, diet versus regular, and we'll test two types of Mentos, mint versus fruity. Now, we're going to run this experiment as a complete randomized design without replication, and what that means is that we're going to test every combination of our factors exactly once. And what that's going to give us is a sample size of 3 brands times 2 varieties times 2 Mentos, or 12. Now, the first rule of design of experiments is to randomize everything. So before we run our experiment, we need to take our 12 trials and randomize the order in which they will occur. So let's do that now. This will help mitigate other extraneous influences on the outcome. For example, I ran this experiment outside, of course, because I don't want messy soda all over my house. And with the local temperature being quite low here, even in the fall, the first bottle was probably a lot warmer than the 12th bottle as they were all sitting outside. If I tested all of the diet first and all of the regular last, the difference in the outcomes I might observe could be due to the variety, or it could be due to the fact that the first half of the bottles were warmer than the latter half. Randomization helps prevent such confounding. For each bottle, we will measure the starting weight, and we're going to put 8 Mentos into it and measure the final weight. I was also hoping to measure the height of the geyser shooting out of the bottle, but even though I had this nifty rope here all marked up and ready to go, the measurements were too imprecise to actually use in the analysis. Also, I kind of messed up the video recording when I was outside, and I really don't want to have to do all this again, so we're going to stick with measuring the weight change. Now that everything's ready, let's go run an experiment. All right, so the first implementation failed miserably. I couldn't get 8 Mentos into the bottle fast enough by hand before the geyser started shooting out. So I think we're going to have to engineer a solution to this problem. Let's go to the montage. Armed with our Mentos insertion tube, we can now solve this problem. And I love it when an experiment comes together. And here comes the best part: analyzing the data. We want to fit an ANOVA model to our data, but first we should check the assumptions of our model and look at the data. Creating box plots for our factor versus our response variable, we can see a few things right off the start. 1, the amount of liquid lost on average is highest for Coke and lowest for Western Family. 2, the amount of liquid lost is much higher for diet than it is for regular. And 3, at least based on the box plot, there doesn't appear to be a big difference between the fruit variety and the mint variety of Mentos. We also use Bartlett's test to check for variance homogeneity, and all 3 factors pass the test. Remember that in classic ANOVA, we assume that all factors yield the same variance. And that's not always going to be the case. If it isn't the case, then we would have to either try to transform our data or perhaps take another testing approach based on another method. Now that we've looked at the data, there doesn't appear to be any anomalies or deviations from our assumptions. So let's fit that ANOVA model using the AOV function in R. But first, we have to write down the equation, and we might try to write down that the weight change is a function of brand plus variety plus Mentos. But that would not be correct, and it's a subtle thing to note, but that the variety, diet versus regular, is actually nested within the brand factor, as each brand will have its own formula for its beverage. Hence, what we should actually write is that the weight change is a function of brand with variety nested within it, and then plus Mentos, which is not going to be related. Now, because of this nesting, we're going to need 3 degrees of freedom to test the variety factor instead of just 1 if it were not nested. And recall that these degrees of freedom are the currency of statistical testing. Every degree of freedom corresponds to something that we're going to be estimating and something we're going to be testing. So we need to use them wisely. The ANOVA table resulting from our experiment indicates a couple things. One, that there is no significant effect from the brand or the Mentos flavor on the amount of liquid expelled from the bottle. However, we do see evidence suggesting that the variety, diet versus regular, does affect the results. So let's dig a little bit deeper into that. Within the Coke brand, we see that diet lost an average of 197 more grams than regular Coke, giving us a strongly significant p-value that's less than 1%. Within the Pepsi brand, we see that diet lost an average of 147 more grams than regular, giving a moderately significant p-value of 2.3%. But for Western Family diet, it only lost 97 more grams than the regular variety. This result has a p-value of 8.6%, indicating that perhaps there's something there, but we might need more data to determine if there is a significant difference between diet and regular within the Western Family variety of cola-based sodas. In general, if we want a stronger conclusion, we could replicate this experiment with a second set of 12 trials performed in a new random order. But I'm way too lazy to do that, and it's super cold outside right now, so we're just going to stick with this data. And thus we have concluded that diet gives a stronger reaction than regular, at least in the case of Coke and Pepsi brands, with some weak evidence pointing that way for Western Family as well. However, the Mentos variety, at least in this experiment, and the brand itself do not appear to have any effect on the outcome. Only the variety within the brand is changing the outcome. But before we're done, we could also consider the starting weight with respect to brand and variety nested within the brand. In this case, we get a very strong p-value indicating significant difference between the brands and varieties. And within all brands, we see that regular varieties weigh more than diet varieties by between about 77 to about 96.5 grams. All of these differences are strongly significant due to the low variance in the data. That is, before I actually open the bottle and start messing with it by adding Mentos, they're pretty uniform. There's not a lot of variation, and that means that we can get extremely strong p-values when looking at these closed bottles. And one last thing to note is that I didn't actually consider weighing the empty plastic bottles used by Coke, Pepsi, and Western Family before I discarded them. So I don't actually know if the brand's weight differences come from the formula of the soda or the additives inside or just the plastic bottle itself. But we can still conclude that diet is lighter in weight-wise than regular because it's tested within the brand, and it seems reasonable to assume that a soda manufacturer is going to use the same bottles for all of their products, diet, regular, and otherwise. So this is a great example of a complete randomized design with nested factors. For even more complex designs, I'll see you in the next episode of Design and Analysis of Experiments.